The equations that you see there for the ascent curve uses completely reversed stress amplitude. That means stress amplitude with zero mean loading. That's how the curves were calculated. So, and now we need to model the mean stress effect on our problem in this case. And to model the mean stress effect, we are going to look at a few theories. If we go to our formula sheet, I've summarized them there for you. We have the following. We have the modified Goodman, and we know the modified Goodman works very well for many materials. We have the Gerber equation, then we have the Morrow equation, which is basically a modification of the Goodman equation to look at the true strength at break. Sigma F, you can use true strength at break there as well. If you look at Dowling's textbook, that's the strength at break that you can use there. And that's very good for ductile materials. And then we have the SWT and the Walker methods, which all have the same application region. Now, in this case, we can easily apply this one here because we have the mean and the amplitude. Here we also have the mean and the ultimate tensile strength, the mean and the ultimate tensile strength of the material that's used. If you look at this equation here, the SWT, the Smith, Watson, and Topper equation, for this you only need the stress ratio and the maximum stress to apply it. So what I'm going to do is we're going to just calculate the completely reverse stress amplitude in a small Excel sheet in our report, and just compare the completely reversed amplitudes that are calculated from these for the problem. And then here we have the Walker equation as well. So we need to do some sort of a mean stress correction. And now we're going to start by looking at that. So if we look at we're going to go back. I'm going to copy this table into our report so that we can look at the equations there in front of us. So here we're now going to do mean stress correction and select the theory to do mean stress correction, which is what we're going to do here. And for that, we have now heading 3 again, or heading 3. So these are the theories that are available. My opinion is that for the high ultimate tensile strength that we have, the modified Goodman equation is more than sufficient to calculate the completely reverse stress amplitude sigma AR from the amplitude and mean that we have for every signal and the ultimate tensile strength of the material. So that's one that we can use, and I suggest that we use it in this case just so that I can do manual calculations in front of your eyes. Now, to calculate damage and the number of reversals or the fatigue life at any completely reversed stress amplitude, we need an equation for the SN curve. Now, the equation for our SN curve will look as follows. Now, our SN curve will be modeled as follows. I'm going to the formula sheet because otherwise I need to page severely through your textbook to get to the necessary problems. Let's use this equation here. You can use two equations, this one or this one, it doesn't matter. But I like to use the exponent m, so let's use this one. I'm going to copy it and take it to our formula sheet. So this is the equation for the SN curve that we're going to use. I'm going to calculate m, the slope of the SN curve, and then we're going to use that for any reference point to calculate the endurance. Now, firstly, to calculate the slope, in this case, the slope of the ascent curve will be calculated, it's calculated from the applicable fatigue strengths at 1,001 million cycles as follows. Now let's look at our equation here at the top. First that we're going to calculate is our strength at 1,001 million cycles. I'm going to copy this to the equation here to the bottom so that we can do the ascent curve. Control V. So in this case, we have this equation here, which I can easily write as follows. So I can say sigma ER, Control C, sigma ER is equal to the bending strength, I can put in there, and the bending strength is equal to, in this case for steel, is equal to 0.5 times the ultimate tensile strength. You have this formula. So there's the one that I'm going to use to calculate the point on the ascent curve at 1 million cycles. The point on the ascent curve at 1,000 cycles can be calculated using this equation. I'm going to copy it down here again so that we can have it in one equation. So let's put it here. And then I'm going to replace this formula here. That is the formula for bending. I'm going to copy this equation in there and calculate it in there. Remember, the load modifies for the fact that we have axial loading in this case. So will be that equation there. Now we already have KF accent, we have KF and all these factors. So what I'm going to do now is I'm going to quickly calculate these. Let's see in our MATLAB if we have KF. So what we will have here in this case, we will have, in this case, it will be equal to, now it will be equal to 0.5 times 1050 divided by KF, which was 1.98 if I remember correctly. C size was equal to, I must go to the top. I typed it in my equation here to have. C size was equal to 0.76. 0.76. Let's remove that. That's C size. And let's put the times in here so it looks better. Times 0.76 times C load. C load, let's look, call in my, because this is my memory for the things. C load was 0.7 times 0.7 for C load times C surface. Let's look at C surface. Oh, I can just read it off here to right. C surface is 0.7 times 0.7 times, and then I can go back to my MATLAB. My temperature, C temperature, my MATLAB. C temperature, oh, C temperature was 1, so I'm just going to put it in here. C temperature was 1. So it's times 1 for temperature and times 0.814 for reliability. That's what we have, and we will calculate this as follows. So we can see here that the point on our ascent curve at 1 million cycles is equal to 0.5. I'm going to call it sigma ER is equal to ER. That's a completely reversed endurance limit at 1 million cycles, 0.5 times 1050 times, divided by KF 1.98 times 0.76 times 0.7 times 0.7 times 0.814. 4. And that works out 80.4 MPa. So the endurance limit at 1 million cycles for the notch specimens loaded in axial loading is 80.4 MPa. Call this back here, I just want to see. 80.4, yeah, we can round it to 80.4. Now we can do the same here at the bottom. So this one will become equal to, if I do this, 0.9 times 1050 MPa, that's the ultimate tensile strength. Now that Kf accent was calculated as Kf accent, I don't have it here. It's that ounce there. So let's say Kf accent is equal to ounce, in this case, 1.3724, but we're not going to look at all those. So it's times C load, which was 0.7, times C temperature, which was 1.0, times reliability, which was 0.814. And if I calculate this, I get the following. So here we have sigma AR 10 to the power 3, and that's equal to 0.9 times 1050 divided by 1.37 multiplied by 0.7 times 1 times 0.814. And for that we get 393 MPa. 393. Okay, let's be consequent and give it a decimal point of, well, it's 0. So it's 393.0 MPa. I'm happy with 393 only. So that's the point on our SN curve at 1000 cycles. Now I can calculate my slope. My slope can now easily be calculated. Is equal to this. Now in this case, we will have the log of into, now let's make into 1 million, so that's 10 to the power 3, 6, divided by 10 to the power 3. So that's what we will have. 10 to the power 3 divided by 10, so that, and that works out 3. Divided by the log of, and in this case we have sigma IR1, that's the strength at 1000 cycles, and that was 393.0 MPa, divided by the strength at sigma IR2, which is 10 to the power 6, which is 80.4 MPa. 80.4 MPa, and that is equal to, so I'm just going to put this in MATLAB so that we calculate the slope. That's the slope of our SN curve. So M is equal to the log 10, now this thing works in log 10, of 10 to the power 6 of 1e to the 6 divided by 1e to the 3, and this will be obviously equal to 3 divided by the log 10 of 393 divided by 80.4. 4.35. 4.35. That's the slope of the SN curve that we have. So now that we have the slope of the SN curve and we have a point on the SN curve, our endurance is now given as, our SN curve is now given as follows. Control C. Now we can calculate the number of cycles at any stress IR, right? And we can just use IR1 now they want to use sigma AR. So here we're going to use the endurance limit. So we just use the endurance limit here. No problem. We can also use the stress at, if we use the endurance limit there, this equation becomes, that equation there becomes 1 million cycles. So this is 10 to the power 6. So that's 1 million cycles. And our slope M, we've calculated is 4.35, right? So the number of cycles at any stress amplitude, completely reverse stress amplitude, is equal to 80.4 divided by that stress amplitude to the power 4.35 times 1 million cycles. And that's what we have. And that's for stresses between 0.9 ultimate tensile strength and above the endurance limit, of course. Any stress amplitude below the endurance limit will give us infinite life. And that's the SN curve that we're going to use with the completely reverse stress amplitude that we calculate with the modified Goodman equation and to calculate the damage on the component.